Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to be looking at the ideal mixture. Our goal is simply to define what an ideal mixture means. We've been using an ideal gas mixture as a reference state, but that's not really a very good reference when we're dealing with liquids. So we'd like to relax those rules a bit so that we can have a more realistic definition of what well-behaved means. So we define an ideal mixture to be one for which the volume of a species, the partial molar volume of a species in the mixture is the same as the molar volume of that species as a pure. And similarly, that the partial molar enthalpy of a species in this ideal mixture will be the same as the enthalpy of that species as a pure. Now, this is going to be true for all temperatures, pressures, and compositions. However, it's not truly a function of composition because it must be equal to something that is a function of temperature and pressure only. Now, these are not going to be ideal gas properties. They're simply the pure component properties. So this is why an ideal mixture is easier to obtain than an ideal gas mixture. Sorry about that. So in an ideal mixture, if I looked at the delta V of mixing, that would simply be taking the partial molar volume of the species minus the molar volume for the species and adding that up for all species. In this case, we're doing it for an ideal mixture. And if it is an ideal mixture, this should go to 0 because V sub I im is going to be equal to V sub I, just the molar volume. In a similar way, we're going to have that delta H of mixing is going to be 0. For enthalpy, for internal energy, I can use the definition of enthalpy, H is U plus PV, to get U as H minus PV. And if this delta goes to 0, delta H of mixing goes to 0, and delta V of mixing is 0, then delta U of mixing has to be 0, from which we can kind of back out that the partial molar internal energy for species I in an ideal mixture is the molar internal energy for species I. We also could do something like this for the fugacity of a substance in an ideal mixture. So if we take our definition for the fugacity of a substance in a mixture and apply the ideal mixture rule to it, then I get xi p exponential 1 over RT, the integral from 0 to p of the partial molar volume minus the ideal gas mixture volume. Okay? And this is for an ideal mixture. This will be exactly the same as saying xi times, and all of this is just the fugacity for the pure substance. For the other thermodynamic properties, it gets a little bit more complicated because we are going to have some mixing. These are all they involve entropy, which involves a measure of disorder. And so therefore, the amount of each species will matter. You can derive this either from statistical mechanics or using the definitions that we did in the previous lessons. And in this case, what I find out is that partial molar Gibbs energy for an ideal mixture is the molar Gibbs energy plus RT times the natural log of the mole fraction. A is very similar, and the partial molar entropy in an ideal mixture for a species is the molar entropy minus R ln of the mole fraction. If you wanted to look at this for the entire mixture, then I'm just simply going to add these up for all the various components. And so we end up with these expressions here. You might wish to pause the video and look at those for a little bit just to make sure you agree. We also could do an expression for Z. Now Z is going to be, remember, PV equals Z nRT. So Z is PV over nRT. So if I take my expression for V up here and do the appropriate multiplications and divisions, I end up with this expression here. So I have a similar expression for Z as I do for volume. Next, we want to look at excess properties. Now, excess properties are a little bit weird. They seem like they ought to be those mixing properties, but what this is a measure of the change for an ideal mixture to the real mixture. If I looked at the change of mixing, how much more is it than I expected it to be? So the definition formally is that the excess M is delta M of mixing for the actual mixture minus delta M of mixing for the ideal mixture. Or a simpler form is this here. We also can do this for partial molar excess properties instead of for the total mixture. So for a molecule, one species in the mixture, I can come up with this expression using the definition of partial molar and applying it to our rule up here. We end up that the partial molar excess property is the partial molar property minus the partial molar property if it were in an ideal mixture. This is most important for Gibbs energy. So let's look at this one a little bit, because this is going to be really practical because it gets me back to fugacity. So I have the partial molar excess Gibbs energy by definition is this. But I'm wanting to relate it to fugacities, which means I would like to subtract off ideal gas mixture rather than ideal mixture. So I'm going to add and subtract this quantity here, equivalent to just adding 0, right? This expression I'll just leave alone for now. This here, I can use the definitions of what this is relative to an ideal gas or relative to the pure species by definitions we've obtained earlier. The ln of x terms cancel out, and so I'm left with these. This relates to the fugacity in a mixture. This relates to the fugacity of the pure. These are the relationships. I can use laws of logarithms in order to combine these into this expression. So what we have is a way of defining fugacity in terms of the mixture, in terms of the partial molar Gibbs energy, in terms of the difference in the partial molar volume and the pure quantity volume. In the next lesson, we're going to start looking at how I can actually use these to define or estimate fugacities of various substances. Thank you very much.